Welcome to Design and Analysis of Algorithms class. Today we are going to start our next part in our 4th unit, which is multi-threading algorithms. So till now you have seen what is meant by dynamic programming, and also you have seen some of the applications on dynamic programming like string editing, traveling salesperson problem, all pair shortest path. Likewise you have seen several applications on dynamic programming, right? And this is another part under unit 4, which is multi-threading algorithms. And till now you have seen how to measure the time complexity of an algorithm, how to measure space complexity, and what are all the measures we are having, performance measures. And also you have seen divide and conquer, and you have seen greedy method, and also you have seen dynamic programming, and also you have seen the applications on each and every paradigm, right? Now, till now, whatever the application you have learned and whatever the example you have seen, all are working on a single processor system. Okay, all are working on a uniprocessor system, and basing on the uniprocessor system you are giving the time complexity or space complexity, right? Whereas if you are learning this particular lecture, you will be able to give the time complexity on a multiprocessor system, right? So here till now you have seen all the applications on a single processor, whereas now you are going to see the applications on multiprocessor system, right? So that's why the name is multi-threading. Thread is nothing but a process, right? So multi-threading algorithms. So now in today's lecture I am going to cover multi-threading basics on multi-threading. Now coming to today's lecture, I am going to cover what is meant by, what are the basics we are having in under multi-threading, and what is meant by multi-threading, and also we will cover what are the operations we have to achieve the multi-threading. There are 3 operations, those 3 operations also we are going to cover, and also we will see one of the example called Fibonacci sequence under multi-threading. And coming to the objective. After learning today's lecture, the students are able to understand the concept of multi-threading. So what is meant by multi-threading, and also what are all the operations we are using, and what is the basic difference between uniprocessing and a multi-processing. And coming to the outcome, the students are able to understand, or they are able to acquire the knowledge on basics of multi-threading after learning this particular lecture. Now coming to multi-threading algorithms, right? So now as I said, today I am going to cover the basics, right? So what is the main motivation? Motivation to learn, there should be some motivation, right? So when we are learning any particular lecture or a course, right? So the main motto is, till now you have seen only the serial algorithms or serial processing or uniprocessing or a single processor applications. Whereas now I want to change it into multiprocessing algorithms or multiprocessing applications, right? So until now we have seen serial algorithms, right? They are quite suitable for running on a single processor system or a uniprocessor system, single processor or a uniprocessor system. Now however, the multiprocessor algorithms are ubiquitous. Ubiquitous means there generally happens, okay? Now or else they are generally existed, right? So now multiprocessor algorithms, right? So to, our main motto is to extend the serial applications or serial processing applications to multiprocessing applications. So here I want to extend my application in such a manner that here, as it is running at present on a single machine, single processor, I want to execute on a multiprocessor machine, so that this will be executed as fast compared to the previous one, because whenever we are executing our processes or in our application on a multiprocessor, it will be executed very fast compared to a single processor system. So now to extend our serial models to a parallel computation or parallel processing or concurrent execution, okay, to make it into concurrent execution or parallel processing or parallel computation, here, okay, okay, to make it into a parallel computation, this is must, that is multi-threading is must, right? So now coming to this, how to achieve this parallel computation or how to achieve this multi-threading. So in order to achieve this multi-threading, we must incorporate, okay, shared memory as well as message passing as one of the concept, right. So we have to inculcate the shared memory as well as a message passing into our corresponding parallel processing or multi-threading concept, so that we can achieve the multiprocessing, right. So now coming to the model, right. So symmetric multiprocessor. So here I am showing you the classical multiprocessor system. Here I am having a shared memory, right. So here I am having 4 processors over here, processor 1, processor 2, processor 3 and processor 4, right. So each and every processor is processing some task. Let us consider each and every processor is having some task, and here it is going to be share the common memory. It is going to share the common memory in order to execute all these processors, and that common memory is main shared memory. And here these are all the processors and main memory are connected via a bus. So this is nothing but a bus, right. So via buses all these processors are connected, and here processor means itself it is having some integrated circuit chips, flip-flops, latches, right. So that those we are representing over here, right. Now dynamic multi-threading, as I said here, in order to incorporate the parallel computation, we are using multi-threading, right. So now dynamic multi-threading, in reality it can be used to handle multi-threaded programs on a single microprocessor. Okay. Coming to dynamic multi-threading, so in reality it can be difficult to handle multi-threaded programs. It is very difficult to handle the multi-threaded programs, right. We are going to assume a concurrency platform, that is, here I want to execute the processes or okay, the corresponding applications running in parallel or concurrently. We want to execute all these processes to achieve multi-threading or to achieve dynamic multi-threading. So here I have to incorporate even the concurrency control also. So right, so thus we will assume a simple concurrency platform that handles all the resources. Resources may be related to memory or scheduling, okay, we have to schedule, and also we have memory, and also resources, the hardware resources like printer may be one of the resource, right, and memory will be one of the resource, cache memory or main memory, right. So all these we have to make utilization of all these resources concurrently, so that the overall process will be executed fastly. Now that process is known as dynamic multi-threading, okay. So here we are achieving concurrency, right. So here we are incorporating concurrency control, we are incorporating concurrency control to make our process as a dynamic multi-threading. Now what are the operations we are using to make a dynamic multi-threading, right. So now in order to make a dynamic multi-threading, here we are using 3 operations: spawn, sync and parallel. Spawn, sync and parallel. Now we will see all these operations. So in order to make or these 3 processes, we can also call it as, in order to achieve concurrency control. In order to achieve concurrency control, we are using 3 processes, right. Here, or we are using 3 instructions, or we are using 3 processes. Those are called as spawn, sync and parallel, okay. So here we are in order to achieve the concurrency control, we are utilizing 3 instructions or 3 operations. So the first one is spawn. So now here, whenever we are calling a procedure, the parent procedure may continue to execute in parallel. That is, for suppose here is my parent, okay, my parent node, child 1, child 2 and child 3, okay. So now here what happens is, for suppose I make this corresponding child 1 under spawn, okay. So now what happens is, this parent node need not wait until the whole execution of this child 1. It may run parallelly, and it may execute any other operations also. Here whenever it is given as spawn means this corresponding child 1 is executing parallelly. So that this parent might be busy with some other operation, like for suppose child 4. Okay, so in parallel this C1 is executing as well as this C4 is also executing whenever I am making a spawn. For suppose even here also I am making a spawn. So this C2, C4, C1, all three are executing in parallel, right? So now corresponding to sync. So sync means here the keyword sync indicates that procedure must wait for all its spawn children to complete. Here whenever we are making a process as under sync, so here it has to wait until all the spawn children to execute or to finish their execution. Okay, until they finish their execution, then only this corresponding sync operation starts. So sync is nothing but synchronization, or we can say that. So here the procedure must wait for all its spawn children to complete. All its spawn children to complete. So for suppose here I have here I have one more called CC1, let us consider. So here I am making it into sync. So this will be started only when all these three are only when this one and this one and this one, these three are spawned one, right? When these three are completed, then only this will be started, right? So that is how the sync operation executes. Next one is parallel. Parallel means here this parallel operation we will use whenever we are writing any loops. So in loops we can execute the statements in parallel. So for example, the operation applies to the loops which makes possible to execute the body of the loop in parallel. The body of the loop in parallel. That is, for example, if the body of the loop is having 3 statements, those 3 statements can be executed in parallel whenever we are making that corresponding operation into parallel. Let's recall once again spawn. Spawn means here the parent procedure can execute parallelly, although it is having one spawn children. Okay. So here when called before a procedure, the parent procedure may continue to execute in parallel. Now corresponding to the next one, sync. Sync stands for here the procedure, the sync operation, whenever a particular procedure is called with sync, so in that case it has to wait until the completion of all the spawn children. So here whenever the spawn children operation is finished, then only the sync procedure will be started. Now coming to the parallel. So for parallel operation, so here whenever we are executing loops, so under loops here whenever you want to make the body of the loop should be executed in parallel, in that case you are going to utilize the parallel operation or parallel instruction, right. Let us see an example. As I said earlier, today we are going to discuss Fibonacci sequence. As you are already aware of Fibonacci sequence, so here Fibonacci sequence starts with 0, 1, 1 and then 2 and then 3 and so on, right. So here the first one is fixed and next one is also fixed. So here the logic is nothing but here fib of n is equal to fib of n minus 1 plus fib of n minus 2, right. So the previous one and the most previous one should be added to get the current one, right. So here that I am going to showcase you now here. So here f0 is equal to 0, which is nothing but the 0th term is 0 and f1 is equal to 1, the first term is 1. And next fi can be achieved by taking fi minus 1 plus fi minus 2, that is nothing but fib of n minus 1 plus fib of n minus 2. This is a classical definition of your Fibonacci sequence, right. So now in order to generate this Fibonacci sequence, there is a naive algorithm which you have already which you are learning from since from the first year onwards from your C programming. So here I am just showcasing you the naive algorithm. Okay, this is a naive algorithm. If n is less than 2, then simply return n. Now x is equal to fib of n minus 1, that is the n minus 1th term I am taking it as a x and n minus 2th term I am taking it as a y. Now I am returning simply x plus y. So which is nothing but fib of n minus 1 plus fib of n minus 2 I am returning, and that will be the current current Fibonacci sequence number, right. So this is your naive algorithm or algorithm which is working on a uniprocessor system. Till now we have learned this Fibonacci sequence algorithm and this is working only on a single processor system, right? So now coming to the time complexity, the time complexity is nothing but the time required for for finding the fib of n minus 1 plus fib of n minus 2, and together it is nothing but big of n, right? We have seen already. Now parallel algorithm. So now I want to incorporate the multi-threading into Fibonacci sequence, right? So now this is a modified algorithm which uses multi-threading concept. So here if n is less than 2, then return n. This is simple statement like previous one. Here I am making fib of n minus 1. To find fib of n minus 1, here I am making spawn. So I am making this operation as spawn, which means that this particular statement will be executed parallelly, parallel execution. And even y is equal to spawn of fib of n minus 2, even this is also parallel execution. Now after finding x and y, in parallel x and y are executing, right? In parallel this statement and this statement are executing. Now after finishing of these two statements, then the next statement will be executed. That's why here sync. Sync stands for wait for the results of x and y, because here x and y we are making it as a spawn operation. Spawn operation means here until those two processes are completed, then only the next operation will be started whenever we are giving an operation as sync. So here return x plus y. So this is a modified algorithm which uses multi-threading, right? So now coming to this, to show the multi-threading computation. So how this is internally computed with the help of a DAG. DAG stands for direct acyclic graph. Okay, so here by means of direct acyclic graph, we are going to showcase how these values are computed, okay, under multi-threading. And also what is meant by a DAG? A DAG means, okay, a directed acyclic graph. G of v comma e is a graph where the vertices v are the sets of instructions. Okay, vertices are v. Here the DAG we are going to showcase as G of v comma e. V stands for vertices and E stands for edges. Okay, now we will see how to represent the DAG representation for the Fibonacci sequence with the help of multi-threading. Okay, how we are going to achieve this multi-threading? We are going to showcase with the help of DAG representation. So here this is an example, okay, example algorithm with multi-threading. Okay, here this is a Fibonacci sequence generation algorithm with multi-threading, right? So now initially I am having A, B, C, right? Here I am representing three nodes A, B, C, right? So this is fib of, so here I am going to represent the DAG representation to generate Fibonacci of 4. So now initial thread is A. So here what are the three threads? The first thread is, here the first thread is this one, that is finding the fib of n minus 1 value, and the second thread is fib of n minus 2, and the third thread is returning x plus y. Okay, and the first thread I am showcasing with A, and second one B, and the third one is C. So now I want to measure this fib of 4. So initially my process starts from thread A. So that's why init thread A. Init thread stands for initial thread. Okay, now here A to B we are having a continuation, because here A and B are parallelly executing and A and B are depending. Okay, depending in the sense, to have our thread C, I require both A and B. So A and B both are having some continuation process. That's why here A to B I have one edge called continuation edge. So here I am representing with an arrow, right? So that is a continuation edge. Now here C is a final thread. Why? Because here thread C, under thread C we are returning the result. So that C is a final thread or final solution, right? So now here A and B, which is nothing but fib of 4, right? So now fib of 4, in order to measure this fib of 4, I require fib of 3 and fib of 2, which is the sum of fib of 3 and fib of 2. So here I am having spawn, okay, I am having spawn, and here red represents the spawn, okay, spawn edge. Now fib of 3 and fib of 2. Again this fib of 3 can be calculated by taking the sum of fib of 2 and fib of 1. So here also I am having one more spawn, right, spawn operation. So here I am calling, okay, I am calling, this can also be called as a call edge also, spawn edge or a call edge. Why? Because here we are calling for the other function, nothing but the Fibonacci function, as it is a recursive one, we are calling Fibonacci function with other value, right. So now here fib of 0 or fib of 1, here I am having only a single thread. Why? Here I am having 3 threads, whereas here I am having only a single thread. Why? Because here fib of 0 and fib of 1 are having the direct solutions, right. Whenever I am giving fib of 0, it is giving me solution called 0, right. Fib of 1 means 1. So which are direct solutions. So that's why, or else simple solutions, or else small sub problems. So for all the small sub problems, we will be having only a single thread called A. That's why, which is fib of 1. Now here also fib of 1 and fib of 0, as there are as these two are the smaller sub problems, I will be having only a single thread. Now after getting getting spawn operations of these two, here I have to return the sum, right. I have to return the sum, or I have to return the values. So in order to return the fib of 1 value and fib of 0, I am representing with yellow color, right. So now whenever I am returning, so that return value will be given to this C. Why? Because here return x plus y, so which is thread C. So even here also I have to return from C to, here also I have to return from this to this, as well as from this to this, as well as from this to this, and from this to this. So finally I will be having the final solution in this thread C, right. So now I am going to showcase again. So here we are having A to B. So fib of 2 means again this will be spawned to fib of 1 and fib of 0. Again here also I have to send back the solution from fib of 1 to this C, and even from this thread to this C, right. So like this, and finally I will be sending the solution back to this C. So then we will be having we are going to find out this Fibonacci sequence by using multi-threading approach, right. Now here yellow one represents return edge. So here in this diagram you have seen several types of edges also, which is initial thread, continuation edge, and return edge, and a call edge, right, and even the spawn edge. This is spawn edge, and here this is continuation edge, and this is return edge, right. So now we are going to learn all these types of edges, right. So now edge classification. So first one is a continuation edge. Continuation edge means here there is a connector from one thread to another thread and within a single process. For example, u comma v. Then there is a continuation from u to v, u process to v process. Then in that case I have to give a continuation edge. So here a continuation edge u comma v connects a thread u to its successor v within the same procedure instance. That is, in your diagram you have seen A to B, because here there is a continuation process from A to B. That is why here we have shown with continuation edge over there. Now next one is a spawned edge. Spawned edge means when a thread u spawns a new thread, when a thread spawns a new thread. So when a parent wants to begin with a new parallel execution of another operation, so in that case we are giving a spawn edge. Next one is the call edge. Call edge represents normal procedure call, nothing but fib of 4 to, in order to find fib of 4 I am calling fib of 3 and fib of 2, right. So there I am representing with a call edge. Now return edge. Return edge means here in every procedure I have to return the corresponding values, right. Whereas your C thread is in your previous example the thread C represents return x plus y. So here I have to return some value, right. So in order to return the value to the previous thread or the parent node, here I have to use a return edge. Now coming to the summary, today we have seen what is meant by multi-threading and also what are all the basics we have. For suppose here how to achieve the concurrent execution or a parallel processing within a application or within an algorithm, how to achieve the parallel processing. Till now we have seen only the single processing of applications, right, on a single processor. Now we are going to see all our applications on a multi-processor, right. So now how we are achieving this we have seen today, and also what are all the basic operations we are using. The basic operations to achieve concurrency control are spawn, sync and parallel. Those three also we have seen, and also we have seen example called Fibonacci sequence. And also in order to depict this concurrency control, here we have in order to represent this concurrency control, how to achieve this concurrency control for Fibonacci sequence, we are depicting with a directed acyclic graph for that Fibonacci sequence. Even that also we have seen today. Thank you.